When you think about the world's most advanced technology, what comes to mind? Probably some crazy complex code, right? But what if I told you the secret language behind it all is actually simple math? Yeah, the same stuff you saw in high school is what unlocks the power behind everything from quantum mechanics to modern cryptography.
Take quantum computing. It's totally mind-bending. A regular computer bit, it's either a 0 or a 1. That's it. But a quantum bit, or a qubit, it can be both at the exact same time. So what that means is when you add more qubits, the power doesn't just add up, it multiplies. It grows with this explosive exponential force.
Just look at this number. That's over a quadrillion. And get this, that's the number of states, just 50. That's 50. 50 qubits can handle all at once. It's 2 to the power of 50. I mean, how on earth could anyone even begin to work with a number that massive? Well, here's the secret. They don't. They don't try to wrestle with that giant number itself. No way. Instead, they use a seriously powerful mathematical toolkit. See, to tame these absolutely astronomical scales, we need to get fluent in the universal language that describes them, the fundamental laws of exponents. Okay, first up, the universal laws of power. And please, don't think of these as some dry, boring formulas from a textbook. This is more like the grammar of growth. It's the language we use to talk about everything from the tiniest subatomic particles to the entire cosmos. So this table right here, this lays out our 4 essential shortcuts. When we're multiplying numbers with the same base, the product rule lets us just add the exponents together. Super simple. When we divide, the quotient rule lets us subtract them. It's a huge time saver. Then you've got the power of a power rule, which is when an exponent is itself raised to another power, you just multiply them together. And last but not least, the negative exponent rule. I know it always looks a little weird, but it's actually just a really simple instruction. Right, so a negative exponent has absolutely nothing to do with negative numbers. Just forget that idea. Think of it more like a flip instruction. It's just telling you to take the base and move it to the other side of the fraction line. So x to the power of negative a just becomes 1 over x to the power of a. That's all it is. A simple instruction for inversion. Now, let's flip the coin and look at the other side. If exponents are all about scaling things up, while radicals are how we zoom back in, they're the tool we use to find the fundamental root of a number. It's kind of like how physicists are always looking for the foundational state of a quantum system. And here is the key insight, the big secret really. Radicals are just exponents wearing a disguise. That's it. A square root, that's exactly the same as raising something to the power of 1/2. A cube root, power of 1/3. They are not two different ideas. They're the same idea, just written in a different way. So how do we actually work with these things? Let's try to simplify the square root of 72. First thing we do is factor it, and we're hunting for the biggest perfect square we can find inside it. For 72, that's 36. So we split the radical into the square root of 36 times the square root of 2. And since we all know the square root of 36 is just 6, we can pull it out, leaving us with a much cleaner, simpler form, 6 times the square root of 2. And this is why simplifying is so incredibly important. I mean, at first glance, adding the square root of 50 and the square root of 18, it looks impossible. But once we simplify them, we find out that the square root of 50 is just 5 root 2, and the square root of 18 is 3 root 2. All of a sudden, they both have a square root of 2. They become like radicals, which means we can just add them up. 5 plus 3 gives us 8 times the square root of 2. Easy. Okay, this is where things get really, really cool. We can use these simple rules to find these beautiful, predictable patterns hidden inside what just looks like total chaos. And this kind of pattern finding, it's absolutely crucial when you're dealing with complex systems, whether that's a tough math problem or the behavior of a qubit. For instance, take a look at this question. What is the very last digit of 7 raised to the power of 2024? I mean, your calculator would literally overflow trying to compute this. It seems completely unsolvable, right? But it's not. We just have to look for a pattern. Let's start small. 7 to the power of 1. Well, that ends in 7. Easy enough.
Okay, 7 squared is 49. We only care about that last digit, so that gives us a 9.
All right, what's next? 7 cubed is 343. So our last digit is now a 3. Are you starting to see a pattern yet? 7 to the 4th is 2,401, which ends in a 1. And what happens if we multiply by 7 again? Well, 1 times 7 is 7. We're right back where we started. The pattern repeats itself. So we've found the code. The last digits of the powers of 7 follow this repeating four-number cycle: 7, 9, 3, 1. To solve our huge problem, all we have to do is figure out where in that cycle the 2024th power lands. And the way we do that is by dividing the exponent, 2024, by the length of the cycle, which is 4. The remainder is going to be our treasure map.
And here's the solution. 2024 divided by 4, it works out perfectly. It goes in 506 times with a remainder of 0. Now, a remainder of 1 would be the first digit, 2 the second, and so on. A remainder of 0 means we landed exactly on the last number of a cycle, and the last number in our 4-digit pattern is 1. That's it. That's the answer.
So we've seen how these rules can help us just crush a tricky math competition problem. But let's bring it back to where we started, because this is about way more than just quizzes. This is about a fundamental way of thinking about the world. Here's one last classic problem for you. Which is bigger, 3 to the 20th power or 2 to the 30th? Trying to calculate those is a total non-starter. But remember that power of a power rule? We can rewrite both of them to have a common exponent of 10. The problem then turns into comparing 9 to the 10th power versus 8 to the 10th power, and suddenly the answer is just obvious. And this right here is the whole point. The logic we just used, finding a simple pattern hiding inside a massive, messy problem, that is the exact same thinking scientists use to manage the mind-boggling scale of quantum computing. It's not about wrestling with complexity. It's about taming it with simple, elegant rules.
Which kind of leaves us with this one big final thought. If a few simple rules of exponents can crack the code of these ridiculously huge numbers, it really makes you wonder, doesn't it? What other problems out there that we think of as unsolvable are really just hiding a simple pattern, just waiting for someone to find the right way to look at them?